Okay, welcome everyone. We'll get started now. Um, so what we'll be doing primarily in this first lesson, I'm going to try and cover in the beginning, just kind of skim through his stable diffusion with diffusers notebook, or just the beginning part of it, where Jeremy goes through some of the just what you can do with stable diffusion, kind of get an idea of the what is done with the program, and then most of the rest of today's lecture, I'm going to follow a blog post by kind of friend of this this particular lesson and ex-attendee of a lot of the TWIML courses, that I named Rekho Prashant. He has a very good blog that makes it easy for us to follow along as Jeremy explains the basic components of the stable diffusion algorithm, if you will, or the stable diffusion capability. And then we'll end by also quickly going through lecture, I believe it's 9B, which covers, again, at a high level, the mathematics of diffusion. As is typical with the fast AI courses, Jeremy typically starts with a high level overview where the math and the details aren't that important. He has repeatedly kind of pointed out that his way of teaching is somewhat different. He starts at the top. It's almost like if you're learning to play cricket or baseball or your favorite bat-based game. He is the example of getting started with just, well, you just need to hit the ball with a bat and run around the bases or run between the wickets. And, the rest of it you figure as you dive deeper or as you play more. So that's going to be kind of our approach as well today. And pretty much after the first couple of lessons, he starts from the bottom and begins building up the capabilities that we need in order to understand all the details of stable diffusion. So that's kind of what the lay of the land is going to be for today. And I believe it will take most of, excuse me, most of the time that we have allocated. Feel free to jump in and stop me and or ask questions, and or I know some of you are more expert at some pieces of this. I don't claim to be an expert as much as just trying to learn. So if there are comments, clarifications, suggestions that you would want to offer as we go through, feel free to jump in and make those comments. Any questions or thoughts before we get going? Okay, one more request. I'll repeatedly make it and also make it on Slack. If you can, please volunteer. I wanted to kind of get it kick-started by doing the first couple of lessons, but obviously I won't be able to do every single one of these as we move forward. So a request to sign up. I posted the Google Sheet. If you cannot access it, let me know on Slack, but if you could, then please go ahead and volunteer to lead these sessions. Today and next week, I'll be doing that. But if any of you are interested, I would request you to please sign up. It doesn't take much to just go through the content a priori and then help lead the rest of us through the lesson. So that's a request to sign up. And with that, let's get started on the first lesson. Let me know if and when you can see the screen that I'm sharing. I think you ought to be able to see it now. Can you?
We can see it.
Okay, great. So this is the first notebook. I'm not going to run the notebook. I mean, you folks can do that. It'll take a little bit of time and rather than waste that, because most of the lesson, as I said, is going to be getting an intuitive understanding of the components and the math. Even the math, it's kind of a lot of hand waving and notations and symbols rather than getting into the nitty gritties of the math. But again, as I keep repeating, it's more to get a feel for and an intuitive understanding of the pieces and recollect those things than getting into the very detailed pieces, and that we'll do during the rest of the course. So in the early part of the lecture, he kind of just installs the various component diffusers, transformers, fast forward diffusers from Hugging Face, which is where most of the usage of the software or the libraries that he uses are all stored in Hugging Face, uploaded in Hugging Face as well. Then he kind of, and again, if you've used Hugging Face, as I know several of you are very familiar with it, you just create a pipe, and if you're familiar with FastAI, a pipe is similar to a learner in the sense that it kind of puts many of the components together. The model, the floating point format, which is FP16, moves it to the GPU. It shows where it is in your local, if you're running it in Colab and stuff. And then he uses a prompt to provide to the stable diffusion algorithms, and then you provide the prompt to the pipe, which is just, as I said, the equivalent to a FastAI learner, and then seek to get the zeroth image provided as an output from the pipeline. Think of the pipeline as, at this stage, just a series of steps that the algorithm takes. And out of that, you get image because the prompt that you're provided is a photograph of an astronaut riding a horse. So that's a pretty remarkable thing that the algorithm is able to do, given that we have just provided a textual prompt and basically nothing else as input. Of course, if you want repetitive, if you want to be able to repeat it and get the same image time after time, you kind of use the seed by setting the seed to a particular value. That enables you to always get this particular picture. If you didn't do that, you might get different variants or different pictures each time. Now, obviously, one of the things which we'll get more familiar with as we go through the rest of even this lecture is the fact that this particular image is not produced, so to say, instantaneously, but through a series of steps that the algorithm takes. And those series of steps are unfortunately called time steps, but they have nothing to do with time, as we'll see as we go through the math and also as we go through the explanations. But be that as it may, I think you'll see a reference to time steps. These are just, think of them as just sequence of steps that you take through the algorithm, nothing whatsoever to do with time. And then early on in the algorithm just spits out something which doesn't look much like anything that we can relate to. It's just essentially noise, but oriented towards the prompt that we provide. And as we see here, what he's showing is the fact that early on in the process, this is step 3. You see a bunch of noise and a bunch of colors, but nothing that you can make out. If you've taken, say, 16 steps through the algorithm, you get a little better understanding, but there's still a lot of stuff going on that isn't directly related to or isn't precisely what we would want from the algorithm. You can see colors that are different. The leg is kind of bent out of shape. There's a bunch of stuff over here which isn't quite explainable, and so on. And therefore, we come to kind of what is known. Some of these terms, again, as I said, since they're looking at it from a high level, we just get introduced to it without a lot of explanation, something called classifier-free guidance. Think of it as an ability to guide the output of the algorithm closer to the prompt that we are providing. That's kind of what the classifier feed guidance term is supposed to enable us to do. And so it's just a method to increase the output and to behave more like the conditioning signal, which is the prompt that we use. So if we do that, and there are various values you can set it to, and down below he prints out a series of the images with the values of the classifier free guidance set to different values. So the first row is set to 1.1, the second is set to 3, the third is set to 7, and the fourth is set to 14. And as we increase the numerical value of the classifier feed guidance, we'll find that the image output begins to adhere, as he says, or at least get closer to the prompt that we provide. And the lower the number, the farther away the image is from the prompt that we provide. And it seems for this stable diffusion algorithm, I think somewhere it says around 7 or 7.5 seems to be ideal. The reason for that, and why not higher the better, and why not just choose 14, is as we get closer to the larger numbers of 14, 16 and stuff, the variation in the image tends to reduce. So at least to me, it seems a little like the temperature parameters, if you're familiar with language models and stuff, where temperature you can use to vary the words that large language models, or basically language models, like spit out, and they're more variant depending on how high or low you set the parameter to be. So you can think of classifier feed guidance, if you're familiar with language models, as kind of equivalent to the temperature, in that there is more variation from the prompt you provide. In this case, as the classifier feed guidance has lower values, you can see in the first set, when it's 1.1, it's the algorithm's attempting something. Sometimes it gets it right. Sometimes it seems just like a jumbled image of something that it's attempting, but nowhere near an output that we would say corresponds to the text prompt. And you can see even at 3 or 3.3, you can see that the series of images begins to resemble what we would like, but there's still some issues. You can see weirdness in how the leg is bent. Even here, the legs aren't quite right. Same thing here. And you can see around 7, it begins to do a really good job of getting the images to correspond to what we want. And then at 14, it kind of gets really good. And then he also talks about negative prompting, which is to say you first provide a prompt. So this is in the output of the algorithm, which kind of gives in the color, in the style of Vermeer. So you can see it's classic blue. I think not much on artist, but I believe one of his famous paintings is the lady with the pearl earring, and yeah, this particular color of blue prominent in that painting. So it kind of prints to color of some kind. And then if you say negative prompt, which means you basically want the blue from this image to be gone because it's negative. So say, take this image and take away the blue from it, then you get, the black stuff, if you will. So by using the negative prompt, you make it move more in the direction of the positive and reduce the importance of the negative. So this is de-emphasizing the negative, getting rid of the negative and emphasizing the positive, if you will. And then, of course, we provided thus far a textual prompt, but that's not necessary. We can do the same. We can use different set of input, an image input instead of a textual prompt, and say, provide us an output which corresponds or is adheres to the image example we have given the algorithm. So we do that by using the image-to-image pipeline of Stable Diffusion, download that from Hugging Face, create a pipe using that, and move that to the GPU, kind of download a particular example of a sketch that Gemini has. And I would, in fact, I haven't done it, but I plan to, is kind of upload, if you will, my own sketches that my daughter made when she was young. And I think it'd be kind of cool to convert some of them to images. So that's an example of something that you can try. And here's something Jeremy did, is, use this of some kind of a four-legged animal with playing with a balloon. Or at least that's what this looks like, but it turns it into a wolf howling at a moon. These images are pretty impressive. And the other thing he shows as well, you can now use this image, and I think he uses the third image, this particular one on the right, and use that and then impose styles of painters on it. Say I want that in the form of an oil painting of a wolf howling at a moon, and you can see some classic Van Gogh style being attempted by the algorithm. So that's something that would be cool to play with as well. And then the other thing he points out is you can do what is called, again, some of these terms, I guess we get to know them in more detail later as we go through the course, but here introduces just like classify free guidance, something called textual inversion, in which you are basically teaching a new word to the text model that the model may not have had already in its vocabulary, if you will. And then what you do is train the embeddings to be close to some visual representation. So in a sense, you're teaching the textual embedding model to create an embedding for something that it may not already have in its vocabulary by kind of fine-tuning that capability. Here in the paper, I believe they're using alarm as an example. And here's, again, what we do is we take the pre-trained Stable Diffusion model, kind of play with it to create an embedding, create the tokenizer. Again, these are things, if you're familiar with language models, you kind of understand that the first thing you do is take, and all of this we'll learn in much more detail. So I know there'll be a lot of questions and we're just skimming through this, but that's top-down approach, if you will. So we don't, in this lecture, get to understand all of the details, but we will do the rest of the course kind of input words, convert them to tokens, convert the tokens in turn to embeddings, which are in essence essentially matrix lookup. And once we've done that and we have kind of done some fine tuning, we can then make the model output something that corresponds to the fine tuning that we have done. And in this case, what he is doing is fine tuning it, fine-tuning the algorithm to be able to provide us outputs which are close to what he calls the Indian watercolor portraits. And you can click on one of these links to take you to an example of what Indian watercolor paintings look like. They're, just like Vermeer and Van Gogh and so on. This is a particular style, if you will, of paintings. And what the algorithm then does is it takes because the Stable Diffusion algorithm is now being fine-tuned to be able to produce these Indian watercolor paintings, it takes the prompt. In this case, the prompt is woman reading is the prompt, but the algorithm has been tuned to style of watercolor portrait. So it kind of understands what the style of watercolor portrait is because of the fine-tuning. And what you get is an image of this kind, which if you check would be a little more in tune with what Indian watercolor paintings typically. And again, not just stable diffusion, but Dreamboot is again another kind of fine-tuning attempt that does something called, that uses again similar to textual inversion. Instead of taking a new token, which is what we did, a token being again something we start with as text and that may not already exist in the vocabulary of the embeddings. So we kind of create an embedding, if you will, from a textual token that we provide. In this case, what we do is we select a seldom used, already pre-existing token from the vocabulary, and that's, we fine-tune the model a few hundred steps to bring that token close to what we would like the image, or we say, hey, make this token that already kind of exists but is not very often used, make that token resemble something that we would like. And so in this case, for example, what he has done is fine-tune the photo of an SKS person, and this SKS person is kind of not, the SKS token, if you will, is not very often used. So we steal that token, if you will, and qualify the person. And so in this example, the SKS token has been kind of fine-tuned to resemble Jeremy Howard. And so when you say painting of SKS person in the style of Paul Signac, again, I'm not familiar with the artist, but I guess he uses a lot of these kinds of, this kind of style, if you will. And so there you see, or there you have it, portraits of Jeremy Howard in the style of Paul Signac. And what we've done is essentially take Jeremy Howard, or actually take SKS person, and instead of SKS, provided our own Jeremy Howard as the input, and then when it says SKS person, by fine-tuning it, we have made it a Jeremy Howard person, and therefore the algorithm spits these images out. As he says, it's kind of finicky and so on. I haven't played with it beyond what's there in this notebook. That's something else, again, worth doing, just to get a feel for how easy it is, or how hard it is to tune some of these things to get the output that we really are after. But again, something that is provided, both the script and the Colab notebook, so you can play with it. Any questions or thoughts on this, just this portion of the notebook? Did anybody try any unique things that people are able to do, or any commentary to add? No?
Yeah,
Okay.
maybe it's like a little early at this point. Maybe we'll see more. I was actually curious about the fine-tuning bits of the the Indian watercolor example, and this one that we see here with the. Is there any details here about how the fine-tuning is done? Because I went through this, but I think I did not go very, understand this very deeply.
Yeah, no, I think, Sujit, that a lot of this he gets into in much more detail in the upcoming lecture. So it's typical of it to kind of, it's almost like whetting our appetite for as they say, the best way to make people learn is to kind of expose a gap and then fill it in.
Right, yeah.
So these things kind of expose the gap of our knowledge, like, hey, how the heck does that work? So now we are motivated to learn how it really works, right? So I think that's kind of his style. And I've often found it, and we've been fooled for so many years on the bottom up. Here is some piece, here is some other piece, but don't worry about how it's used. Let's get you all of the fundamentals, which take like, an entire semester. And then at the end, maybe spend a lecture talking about, well, these are all the ways you use it. His style is the exact reverse. Is, here are all the ways that things actually you can play with, and here are the things that it does. And then let's figure out the details, and we are therefore much more motivated to learn the details. At least it was frustrating the first few times I went to, because I was like, I don't understand any of this stuff, but that's the way he teaches.
Yeah.
And
okay, yeah, all right. We can cover
any
it
other
later.
comments or thoughts?
No, not from me. Yeah.
Okay. Anyone else?
So did anyone try? Yeah, sorry. So I went through the notebook, although I was not able to run it. I tried to run my local PC. I guess that's too big. The pod is too big to even come there. So did anyone try to run it on Colab or Kaggle or Paperspace?
Yeah, I did. This is run on my Colab Pro. I have a Colab Pro account, so you can see, and I also have a Google Drive. So if you see up above this thing, so all these things, I've run it on my Colab account, not right. So in my own directory. So all of the outputs and everything else you see are all from my particular run. So yes, I did do that, and you can do that on Colab Pro. I think, as he says, there's Paperspace and or Lambda Labs or other things. If you are in the US, I think Colab Pro is about $10 a month. And at least because I play around in Kaggle and these kinds of things, it's pretty useful. And at least for this run, I feel Colab provides a couple of different GPUs. I think a V100 and an A100, and usually for Kaggle I need the A100, but for this I was able to get it done in fairly quick time, even using the lower level of GPUs. If so.
Sure. Thanks a lot.
Okay. The next thing we'll do is kind of take you through and again a conceptual or intuitive understanding of the pieces that go to make the stable diffusion. Again, not all the details, and some of it is an approximate and an intuitive understanding. But then again, that's what I like about Jeremy's approaches. When you walk away from the course, you at least remember, or I tend to, each is for her own, but his style of teaching, I really appreciate, primarily because it leaves you with the intuition and the conceptual understandings, which are stronger than just the math and so on. So what we'll do in the next two sections of this lecture is kind of go through the understanding of the components of what are the major components of the stable diffusion algorithm, if you will, and then end with lecture kind of 9B, which a couple of his ex-students and current co-teachers kind of talk about the math. So the next, I don't know, maybe half an hour or so, we'll spend on kind of understanding the basic building blocks. And instead of creating all of this material myself, as I said, I just used the blog post of Rick Hill, because he kind of essentially provides all of the ingredients that we need to, or that I need to help explain, if you will. So to start with, what Jeremy does is say, let's say we have a magic API, right? And that's this function F. And by the way, you can read through, so I'm not going to kind of read, you can read through most of this. So I'll try and just summarize the slides or the pieces as we go through. And feel free to jump in, and also feel free to go through this offline as you have the time. So let's assume that we have an API. The bottom line of all this function or API does is it says, if I provide you an image, let's assume there's a 28 by 28 image corresponding to kind of the MNIST handwritten digits data set. then we can kind of generalize from there. But let's start with kind of a 784 pixel MNIST digital data set kind of inputs. And let's say we have an input which is just number 3, and let's say that we have an API which basically says if I provide you an image, what it outputs is the probability that the image is a MNIST digit. So you can see that when we provide this, it says it's 0.98. When we provide this weird figure, it looks almost like a tree, but nothing like an image. But hey, it looks like an 8 if you squint, and a kid might draw an 8 like that. So it kind of says, well, it's half your way to being a digit, and then this is just seems noisy, so it's a 0.02. Now, why is this thing interesting? Well, let's see. From just having this API, how can we go from something that just predicts whether an input image is a digit to utilizing the API to actually getting a digit? Well, how do we do that? Let's see if something is just noisy, like this X3 input here. One way we could think of using this API or building block is to say, what if I begin to tweak some of these pixels, and all I want, given that the this magic API function, since it gives me a probability, if I tweak the pixels, every one of the 784 pixels in some way, that is, make them lighter or darker. Think of this as a binary black and white image of an MNIST digit. So if I tweak, and by tweaking I mean make some pixels darker, some pixels lighter, and then provide that to this function, does the probability go up or go down? That ought to be some signal that tells me whether I'm getting closer from starting with X3 by fiddling the values of the pixels. Am I getting closer to an MNIST image? Is something that we can use this black box to provide. Because let's say we provide X3 as an input and it just is 0.02. Then we fiddle around with some pixels, and then we provide that fiddled pixel image to the API. And if that API or black box provides an output of 0.023, we say, voila, good move, because we change the pixels in a direction, if you will, that is closer to that of an MNIST figure image. We still don't know what the figure is and stuff, but we are saying, hey, seems to be we are somewhat on the trail of getting to an MNIST image, right? So, so it just gets into the detail of, well, I mean, which pixels do we change? And typically in the digits, we don't have any black pixels at the bottom left corner. So if we make bottom left, bottom right, top right, all whiter and so on, then we maybe get this probability much higher and so on and so forth. So when we are doing that, what we are essentially doing mathematically is trying to compute the gradient of the output, if you will, or the gradient of all the pixels of the image with respect to the pixel inputs. Now, one of the things if you watch the video, he kind of jumps off to make this point is this is a garbage notation. This essentially what he shows here is meaningless in a mathematical sense, because what he actually should be saying is just delta of X3, or if you want to keep the P, you can just say delta of P of X3, which is just the probability, if you will. But you can just say nabla of X3 with respect to all of the pixels of the image X3. So this particular notation where he has del on the top and at the bottom, or nabla on the top and the bottom, is not something that has any mathematical meaning. And he kind of explains that. By the way, if you're interested in the math of the mathematics underlying or the matrix mathematics underlying all of this, I think he, meaning Demi Howard and Terence Parr, have this excellent, I think it's like a 28-page write-up. I'll post a link to this. We also, on this very forum, had, I think, about 3 or 4 sessions of a course that was taught that went through this particular paper, if you will, in great detail. So if you're interested in watching those videos, I can point you to provide the link to that later as well. But this is an excellent paper which kind of gives you in a short form, the matrix calculus that you really need to understand to get a good grasp of deep learning. And in that, he kind of covers the details. But anyway, that's an aside. But bottom line, all we are trying to do is determine how or determine a gradient, if you will, which is how does the full image X3 get closer or farther away from an MNIST digit as we fiddle or tweak the 28 by 28 pixels, therefore the 784 pixels. And the reason that's a nabla is because now when we do that, that is when we fiddle the pixels or change the values, basically what we're doing is taking a gradient of the image with respect to each of the 784 pixels. Therefore, it's a vector. It's a vector which indicates the output change with respect to 784 values, therefore it being a vector. So that's where this particular thing indicates, right? So it says, how does the output image change with respect to changes in 784 values of paper pixels? And then what you do in this process, because we want to get closer to an MNIST digit, is after making the change, and if we see the probability of that output of the black box increase, we say, oh, this is good. So what we then do is we multiply the gradient that we have just gotten with some kind of constant. Think of it as, if you're familiar at all with the basics of deep learning, it's essentially like a learning rate, but some kind of constant. You multiply the gradient by a constant and you subtract that value from this original image that you started with. And therefore what you have done is you start with some thing which is really noisy, something that doesn't look at all like an image, take its fiddle with its pixels, which essentially is equivalent to creating a gradient, make sure that the gradient is, or the output of the black box says the probability is higher, multiply this gradient then that you obtained with a constant, subtract it from this image. So now the resultant output that you've gotten, which is X3 minus the constant times the gradient, is a little bit closer to your desired output of an MNIST digit. Now you can begin to understand this steps concept that stable diffusion has. So if you continue to do this for a while, then your X3 output, that's X3 prime or X3 double prime, 3 primes, whatever, will begin to get closer, if you will, to an MNIST digit, right? So you kind of pass this new image to a magic function and you get a new score and you repeat the process. So what we can do by this is changing the pixel one at a time and then kind of calculating the derivative and stuff. You can go towards improving this image, which began as a noise, and get it closer and closer to an MNIST digit. So what we have now achieved, if you will, is just from having a neural network which tells us the probability of an input image being high or low of an MNIST digit, that is the probability of an input image that we provide, the network says this looks like an MNIST image, or it has high probability of being an MNIST image. Just from that capability, we are now beginning to get the ability to generate an output from just noisy input to a desired output, which is, in this case, we have fixed it to be MNIST digits, right? Now, we want to train this neural network, right? You just said this is what the neural network does, but we haven't yet kind of established how we would train the neural network. So in order to train the neural network, what we do is we provide it a bunch of inputs, if you will, as usual, supervised learning. So we provide a bunch of inputs and allow the network to then, because we don't have, again, a good core function or a good function which tells us how do we measure whether an input image is a good MNIST image or not. We don't, coming up with something like that, which precisely measures whether an image is like an MNIST digit is something very hard to comprehend. So it says intuitively, let's just think of this network as something that predicts the noise in the image. So that's what these right triangles are. And the left is the actual MNIST digit, if you will, that's buried in the image along with the noise. So what we do then to train a neural network to produce something that we want or to get us towards identifying or generating the probability of an image being close to an MNIST digit, what we do is train it with a bunch of images, some of them having less, some of them having more noise. So less noise to high noise, and having digits, if you will, and have the network predict the noise in every image. So in case of the first image, there's very little or no noise, 7, little noise, 3, little more. This is pretty much very noisy, right? So what we do here then is to say, all we are doing is provide a bunch of inputs, some of them noisy, some of them less, some of them more, some of them with no noise. The neural network is trained. Let's assume that the output or the loss function that we use is essentially mean square error of the noise. So it's the predicted noise versus the actual noise in the image. And let's also make an assumption that the noise is a Gaussian distribution. So it has, a mean and a variant, and this n with 2 inputs that is shown here is essentially saying that the noise that we use or that we add to these images is a Gaussian noise with a mean of 0 and some amount of variance. So let's say that the neural network inputs are these images. The output is basically the noise in the image. That's what the neural network provides. So one of the key things, we have one building block, if you will, which is a neural network, input of which noisy images, output of which the noise in the image, and the loss is essentially MSE of the noise, right? So that is essentially our neural network. And if that is our neural network, then what we can do is do this repetitive, iterative subtraction thing we talked about, where we multiply the noise that the network predicts is in the image by a constant value, subtract it from there. That will then make this noisy 7 closer to the actual 7. And we repeat that, multiple times and get closer and closer to the digit 7 that we want, right? So this then is the first building block of our stable diffusion algorithm, a UNet, and you can kind of look up what the UNet is and its structure. These are some things that is covered in the part 1 of the course, but again, it's not at this point essential to understand all the details of the UNet. You can look it up offline, but think of it as just a neural network that's good at predicting the noise in an input image. So you provide an input image, it predicts the noise, and you go through this process of subtracting a constant value from the input of the output of this, which is the prediction of noise, right? And you can kind of check online details of UNet and what it's typically used for. So you can see this building block has an input, as I said, of a somewhat noisy image, and the output, which it predicts of the noise. Okay, so that's one of our very critical building block of stable diffusion. So again, we have of course simplified this and used an MNIST image, but in the real case, in the cases of what we saw already, right, like the astronaut on a horse, or the Jeremy Howard picture, or the painting in an Indian watercolor style, and so on, those are images which are much bigger and much more fine-grained and beautiful. Those pictures are typically 512 by 512 by 3 sized. So this, I believe, is, if I'm not mistaken, 16:7. I forget the exact number. I think he provides it here. 786 432 pixels when you have image of this size. So that is actually a very large number of pixels, right? So do we really need all of these pixels in order to kind of get to where we are going? Well, already some of the capabilities that exist in our world provides hints to us that that's not really needed. Why? Because if you can, if you are familiar somewhat with the history of digital imaging and stuff, the whole JPEG algorithm says, well, we do not need all of the 512 by 512 by 3 or 786,432 pixels. There's a lot of stuff in those pixels that you can somehow encode and reduce the size of what you need to transmit in order to regenerate the exact identical image. So you don't need all of the pixels to be communicated or transmitted, if you will, and that's the JPEG algorithm and so on. The JPEG picture is far fewer bytes than all of the bytes needed to represent every single one of these pixels. So how do we then reduce the computing need, if you will, and not have to deal with 786 432 pixels? So along comes this concept of a variational autoencoder. Again, a term that is, something that we'll get into a lot more detail. He explains the math and what it does and so on in great detail. At this level, we just need to get an intuitive grasp of what it's able to do. So essentially what an autoencoder does, as we'll see in the next several slides, is it takes this very large image, 512 by 512 by 3, shrinks it into a much smaller value, which is essentially an encoding. And you just take a bunch of stride 2 steps, thereby, reducing the height and the width of the image. So here you've reduced it by 2, increase the channel width, channel depth, by 2. So you go from 512, 512, 3 to 256, 256, 6. Then again, by 2 reduction, 128, 128, and then 12, 64, 64, 24. And then you just use kind of, I believe, a ResNet of and bring it down to just a channel reduction stuff. So you go from 64, 64, 24 to 64, 64, 4. So if you do the math of the 64, 64 by 4, that is, if you will, a 16,384 pixels. So by doing these steps, what we have done is we've taken the 786, 432 pixels, reduced them to 16,384, a 48x reduction. But keep in mind that this output of what we'll call an variational autoencoder, and the variation part we'll get into later. But basically, what this does is it encodes these many pixels, if you will, which is a very large number, into a 48x smaller number. But all, if not most of the information contained in this image is still encoded in a much smaller amount of pixels. Right? So then what you do and the reason for the name autoencoder is you can now take this smaller encoded value, blow them up as you go back through a similar but opposite process. So you go from 64, 64, 4 to 128, 28, 12 to 6, and then get back to 512, 512, 3. you just build this network. This is not a UNet, but this is an autoencoder. And then what you do to make sure that your output image resembles the input image, you again train this network by creating a loss function, comparing the input and the output and making sure that this loss is as small as you can possibly get. When you do this and you train it on millions of such images or millions of images that you can get off the internet, then what you have, this entire network is called an autoencoder. The name auto comes from the fact that, basically you're providing an input, and what it does is it spits out the output. And keep in mind that our goal for training the network has been the output is equivalent to the input, and we reduce the MSE between these two. And so essentially we kind of train the network to generate an output which is equal to its input. And when we do that, then the top half of the network, the green highlighted portion here, is called the encoder piece of the autoencoder, and the red portion down below, which converts the encoded output into the original, back into the original image, is called the decoder. So think of the top as the encoder piece of the autoencoder and the bottom as the decoder piece of the autoencoder. And again, conceptually, what we need to take away from this discussion is an autoencoder is something that just converts an output or generates an output equivalent to the input that we provide. And it has two pieces, an encoder and a decoder. The encoder shrinks or compresses the image. In this case, it's an image, so we'll talk about images. And the decoder regenerates the large output that we originally submitted as input. So the output of an encoder will be encoded and therefore a compressed value of the image. The output of the decoder will be the original image and therefore a much larger value. So we'll start, in case of the encoder, with a large input and a small output, and the decoder will be the reverse of that. We start with a small encoded compressed value, and we'll get back a large uncompressed value, if you will. Right? So that is the second of the building blocks that the Stable Diffusion uses, which is an autoencoder. And what we do is, instead of providing, the gigantic large pixel value of our image that we want to kind of that we want to use to train our network, we provided what are called latents. And you can think of the latents as essentially things that are the output of a autoencoder's encoder. So instead of taking these images, which are the beginning large values, 786, 432, we create latents, which are these smaller values, 16384. That's what is provided to the first building block we had, which is the UNet. And the output, the UNet still provides the noise in that image. So instead of providing these gigantic images, we provide these so-called, and again, jargon here, but basically the latents, and think of latents as compressed noisy images. So these are the latent noisy images. So again, the inputs and outputs for the UNet now become somewhat noisy latents. Remember the picture of, the 9, the 7, the 3, and the 6, and so on, with various levels of noises. But instead of them being original images, these are now compressed noisy images. So that's what, instead of using compressed, we say latent. So latent noisy is the input. The output of the UNet, as always, is still the noise. But that's where the VAE comes in. And again, keep in mind, as he says through the rest of the course, or this is a desirable thing. You can do it if you had all the computing in the world and didn't have to worry about computing and time and all these things, then and money that we need to spend to train the networks, then you wouldn't care about using VAE and compression and noisy latency. You could probably get away with just using the original image, but pay a steep price for it. But in the practical world, all these things matter, so we use the VAE encoder. Right. So that's the second big piece of what we have as part of the Stable Diffusion. So the first piece was the unit, which predicted the noise. Now, instead of providing the actual image to the unit, what we do is take a variational autoencoder, shove the image through it, get it encoded, or the noisy latents. The noisy latents are what we provide to the unit, and of course, it still predicts the noise that's embedded in the latents. And as he says here, keep in mind that this is an optional building block. We use it because it can help with smaller latents, and so it's much faster. And of course, this is only required when we are training the network, training the unit to do what we want. When we do inference, we already have the trained network, so we just provide the actual image. Okay, the third piece, which is also important, because keep in mind that when we saw the usage of it, we actually provided textual prompts. So we didn't just provide image, we kind of provided a textual prompt and got the stable diffusion to generate an image. So how does that, or what is the component of stable diffusion that allows or enables us to do that? That is the clip. And I think, in fact, I believe, Sujit, you have much more familiarity with the whole clip algorithm and paper, if I remember correctly. I think it's
Mayank can on the team.
Yeah, so you can correct me, but in this case, again, it's just more of the how do we use it in the algorithm. So he kind of, again, provides a more intuitive feel for it rather than getting into the details. But again, you get them to read through the clip paper and figure out what all is going on there. But essentially, think of it this way. If instead of just providing the noise to the original unit and having it predict the noise, and suppose we know, and we actually do know, as we saw previously, what is the number that's embedded in the noise that we are trying to get at? And because we know that, why not provide that as an input as well as the image? So what you can think of is, let's say we one hot encode, and again, because the digits are 0 to 9, so you can one hot encode the input into like a 10-digit one hot encoded value. In this case, 3. So you just turn on the bit 3, 0, 1, 2, 3, and then provide that as an input along with the image to the unit, and have the unit predict the noise in the image. Now, in this case, the important thing to realize conceptually is, because you're providing more information, meaning you're adding the digit value to the noise or the image that you're also providing. So this network, in a sense, is getting more information. So it ought to get better at predicting the output, better at predicting the noise, and better at predicting the noise in the image versus the actual value, if you will, of the MNIST digit, or it's not so much the value as much as, the one hot encoded value, which is the digit 3. So essentially what we have done is just added something to the input. The output of the unit network is still the same, right? It's still the noise in the image. But in this case, we are now enhancing, if you will, the input, which is providing the digit, which is one hot encoded. But again, keep in mind that what we are actually after is all these beautiful images of an astronaut on a horse, a funny Jeremy Howard in the spy loft, and all these kinds of things, right? So it's somewhat impossible, if you will, to one hot encode every concept that human beings can come up with, rather than this narrow field of just 10 values of MNIST digit. So it's okay in a sense to play with one hot encoding MNIST digits, but how the heck do we translate that into, communicating concepts about images to our entire network of algorithms, right? That is very hard to do. So the way that problem is resolved by, I believe, the clip paper and so on, is to say, well, let's take all these images that are hanging around the internet. Many of them these days also have an alt value, which is, for providing a textual description of what the image is. And we train the network or train a network in order to, first we kind of generate an encoding of the text and an encoding of the image. So independently generate two encodings, one which corresponds to the text. So let's say this is a swan. So the alt text says it's a graceful swan. The image says it's a swan. I shouldn't say says, the image indicates that it's a swan. The text says that it's a swan. What we do is convert through a text encoder and an image encoder and get an embedding for a swan and an embedding for the picture of a swan. And then these are the details that are explained in the clip paper. What we do is, one way this can be done. And again, this is just a simple explanation. It actually may be a much more complicated or complex way to do this. But what we're trying to do is to say, if we take the dot product of these two, we want the dot product to be a small value. And what making the dot product of two things to be a small value intuitively stands for is making these two embeddings be in some high dimensional space. The dimensions of the space depend upon how big this encoding size is. But in that high dimensional space, by reducing the dot product of these two embeddings, what we're actually doing is making sure that these two embeddings, the textual embeddings, which is the textual description of the swan, and the image of the swan, the embeddings of those two things should get very close to each other. That's what we are trying to accomplish intuitively by reducing the dot product between these two embeddings. So again, step back and take a quick walkthrough of what we are trying to do. What we are doing is taking an image, taking a textual description, creating embeddings for those two, and then making sure that by taking the dot product of these two embeddings, that we are in this high dimensional space, the dimension determined by the size of this embedding, making sure that these two embeddings get as close to each other as possible. So that's what this process is. And for each of these images, the corresponding textual description is provided in kind of a table. And let's think of it this way. Anytime that the two match, which is, graceful swan is what this image describes, then we want the output, if you will, to be high. So along the diagonal of the matrix, we want things, because they match, to be very high, and everything else where it doesn't match to be low. And that process is essentially a contrastive loss process. And so you can think of it as essentially the reason for the paper being CLIP is contrastive loss. I forget now what IP stands for, but basically what we're trying to do is maximize the case where there is a match and minimize the cases where there's a mismatch. So by that, we are kind of moving these two embeddings closer to each other and farther away from all the rest of the embeddings. So this process by which we get the images and the text descriptions to get close to each other is what is described in the clip paper. And that's another component of this whole stable diffusion algorithm as well. That's the third component. So again, step back, think through the components. One is a unit which predicts the noise in the noise. Originally, it was the original image predicting the noise in the original image. Later, we used an VAE autoencoder, if you will, optional. But again, why? Because we want to reduce the size of inputs we provide and train and so on and so forth, computing efficiency. So we use the autoencoder to shrink the latents, add noise to the latents, provide that to the input. The noise of the unit, the noise of the image is still what is predicted by the unit. But okay, this is all done so far conceptually with MNIST digit, but let's kind of expand it to think about what we actually want, which is all the concepts in the world, if you will, that can be in images. Along comes the clip paper, which is take a textual description, take an image, kind of using the clip algorithm, make the embeddings in these two, embedding of these two concepts in a high dimensional space close to each other, and through the contrastive loss process, get things which are similar to be close to each other and dissimilar to be farther away from each other. So by doing this, what we are essentially saying is if we say a graceful swan, a beautiful swan, a lovely swan, then what we essentially will get is the textual encoding of all these things will be closer to the image of a swan. And that's what we achieve by the clip process, right? So then it kind of come to the summary of these three building blocks of stable diffusion: a unit, the input of which is a somewhat noisy latence, the output of which is the noise in the latence. The VAE's decoder, which takes the small latence. Remember, this is the backward path, if you will, or the path from the compressed encoded latence back to get to our original image. So the VAE decoder will get small latence and we'll get back to original image. And the clip text encoder, to which we provide the text, and out comes an embedding. And the embedding is something in the high dimensional space, which kind of corresponds to the concept that we are trying to describe in the form of text, but which will create an embedding that will enable us to translate, if you will, quote unquote, from the text to an image. So that's, if you will, the three major components of stable diffusion. Of course, there are various parameters and various ways these are put together and tweaked and so on. We talked about textual inversion. We talked about classifier free guidance. So however, all these things done, that's something we'll learn much more of as we go through the course, but at least the major building blocks of stable diffusion algorithm are the unit, the encoder decoder of a VAE, and the clip text encoder, which we can then guide the unit with the caption. Now, a couple of jargon-related items, and in fact, one of the jargon-related items, or actually I should say both of them, we'll get a much better understanding as we go to the math of stable diffusion in the next segment. But here, let's again get a good understanding of just what these mean. So even though we'll encounter the term score function, essentially what it is, whenever the term score function appears, think of it as the gradient of the image with respect to its inputs. So where we had said nabla of x3 with respect to x3, that is how, if we take the gradient, and intuitively think of the process of twiddling the pixels to get them closer to the MNIST digit. So whenever we say score function, think of it as that fiddling, which in mathematical terms is nothing but taking the gradient of the image with respect to its input pixels. Therefore, that's what is a score function. And remember that a score function multiplied by a constant is what we repeatedly subtract. In essence, closer to the actual thing, what we do is take the gradient of the latent noise, latence combined with noise, and take that and subtract it from the latent input, right? So these gradients is what is often called the score function. The second thing which we, unfortunately, as I said, is time steps. There is no concept of time actually, but the reason for this confusion is the original math behind the whole stable diffusion explanation was differential equations and differential calculus. So in differential calculus, you've kind of been exposed to, Newton-Raphson methods and a lot of iterative methods. Basically, you try to iteratively get to a solution. You don't jump to the solution in one step. You kind of iterate your way there. And those steps that you take along the way to get to a solution, because the math was associated, the original math explanation associated with this process was differential equation. So the terminology that the original explainers used was that of time steps, but essentially think of them as just steps in an algorithm, has nothing to do with time. So another way to think about it intuitively is the time steps aren't time steps, but think of them as steps that indicate the quantity of noise that's added to the image. So if you can think of a noise schedule, So this is T, again, T here, because we use the term time steps, is think of it as steps or sequences or values monotonically increasing along this axis, and the noise that's added to the image or to the noisy latents is what is along the y-axis. So think of time steps as an indication of the amount of noise, and in this, if the noise schedule, that is the amount of noise you add to the latents, is provided by this graph, then this graph says the higher the time steps, the less the noise that you had, and the lower the time steps, the more or the larger the value of the noise. It doesn't always have to be like this. It can be in the reverse shape. It can go up as well. But given a step, you can translate that into a particular amount of noise added to the image. So if you randomly pick a T, then you'll get a corresponding amount given a noise schedule, right? So when we're training, we just need to pick some random amount of noise. And one way to get the random noise is to pick a T and pick up the value based on a schedule, right? So every time we train the unit, we take a batch of images, pick a time step, and pick a noise resulting from that random choice of T, and add that to all the images, and train our network to predict the noise in these images, right? So that's what this describes, right? And so keep in mind that when we are therefore generating a picture starting from pure noise, right? So it corresponds to T equal to, at least in this noise schedule, it corresponds to T equal to 0, right? So it's a very noisy image. So as I've shown the iterative process before, in each case, you allow the network to predict the noise, and then you subtract it. And you can see why we don't go to the end result in one step, because what we wanted to do, or what it's capable of doing, is predicting the noise in the image, which it can be high or low, and then you subtract that noise, get it closer to the desired output, and then we kind of repeat that step multiple times to get to where we need to go. Right, and that's what is described here. You take the constant C, just like a learning rate, but here we're not doing is, or what we're not doing is updating the weights of the network. Instead, we are actually taking the constant, multiplying the gradient with the constant, and subtracting it from the actual input in order to get the output. And a lot of these details of what is the value of C, how much do we subtract, what do we use to control the subtract, those are all the variations that we'll get into in detail. But again, as I keep repeating, this is just conceptual understanding of the basic building blocks, right? And the one other thing which he talks about, which is fascinating, and we'll get a little bit more of this in the next segment of this lecture also, is the fact that original math behind this was a lot of differential equations. That's why you see time steps and so on and so forth. But if you kind of look at the process I've so far been describing, you can think of this whole gradient thing and taking and subtracting values and so on as also somewhat close to an optimization process, and using neural networks to using optimization of neural networks, loss function optimization, and so on and so forth. So one could conceptually say that using differential equation, one way of describing it, but using the math behind optimization and neural networks and loss functions and stuff could be another way of describing it as well. So that's why there is an analogous explanation of this whole process, which could be explained using deep learning concepts as opposed to the differential equation time-based process, right? So there are optimizers, and in the first part of the course, we kind of learned about momentum and Adam, and how we can take a running average, and how if you're moving in a particular direction, well, why not increase the steps in that direction to get to a faster convergence, and things of this nature, if you will. So that's where we'll get into more detail of how the two processes seem to converge. And if that's the case, then as Jeremy says, there are many more concepts that we can potentially bring from the domain of deep learning into the diffusion domain and try different ideas. And those are things that he intends to do and probably has done, because this course was taught in early October of last year, and we are already in May. So it's 6 to 9 months, and a lot of progress was taking place day by day. But that's, if you will, and I would encourage you to go through and read through this blog. It's a well-written blog post, essentially capturing everything in text that Jeremy said in his lecture. And I just thought I'd use this rather than preparing a whole bunch of slides to go through. Any question of this kind of whirlwind tour of an explanation of the building blocks of stable diffusion that we took? Any comments?
Yeah, I think one thing I kind of liked was that, at each time step, he's taking away. So he explains how, using this encoder decoder approach with the unit, he's basically squeezing out the noise, right, in the latent. And basically with the time steps, he starts with the original image with the noise, and then it goes through one step, and then he takes the output and feeds it back in with less noise now, right? So and progressively over time, the noise is removed and the image appears, right? So
yes. Yeah. So it's kind of fascinating that, embedded in the noise is the actual image, and you kind of begin to extract out, if you will, the noise pieces, leaving behind the image that you desire.
One question I have is this: it keeps referring it to the structure as unit without cross connection, and then he says that it's actually variational autoencoder. So it is variational autoencoder. It's not unit. Like, why do we call it unit?
yeah, I thought
It is.
yeah. Sorry, go ahead.
Go ahead, Sudhi.
No, I thought I saw somewhere it's a unit, but then you're right. I mean, it is actually like it's a variational autoencoder. He later points that out. Sorry, yeah.
The network that you train, the network that is trained is a unit. The variational autoencoder is the piece that provides the latence, and then that is used to provide the noisy latence to the unit. So this function F that he talks about here, which is a key piece which actually does the prediction of the noise, is actually a unit as far as I understand it.
So he keeps cross connections.
So I think functionally it's
Yeah.
So structurally it's a unit, and functionally it works as a variational autoencoder. I think that's
yeah. That may be, but my point is it does have the cross connection. The variational autoencoder doesn't have the cross connection. That is just used to convert the input images to the latence when you want to train, because you want to train with the latence. And as he says, the inference network, the stable diffusion network, which we eventually use, which is being pre-trained, is actually a unit, as far as my understanding. And of course, we'll know a lot more about it as we go through the course. But I believe it's an actual unit with the cross connections. Yeah. Any other thoughts, questions, comments? Okay, if not, let's kind of quickly go through the math, because that's fascinating as well. It's covered in the lecture 9B that a couple of his students go through, but I thought I would prepare some slides to kind of put the math intuition behind some of the stuff that we talked about. So far, it's been more in the code or neural network kind of domain that we got into. But now let's kind of go through, again, high-level math, not solving actual equations and stuff, but explaining the mathematical concepts behind the whole diffusion process and linking it to what Jamie has explained so far. Okay. Again, feel free to interrupt, comment, questions, and stuff. So let's look at this. Remember that what we want as the goal is to learn a probability distribution. The reason for now we're kind of switching into math terminology. So unlike code and neural network and stuff, as I said, some mathy discussions and descriptions. But what's our goal? Well, our goal is to learn a probability distribution. A probability distribution can be described as P of something or Q of something, typically P, but there's a reason why we are using Q here that will become obvious in a couple of slides. Let's say the probability distribution that we want to figure out is that of an MNIST digit. Again, I wasn't able to, it's too lazy to be able to add a noise and make it transparent and stuff, but just imagine noise around the figure 8. And that's the probability distribution that we want to discover or generate, if you will. And let's say the image, much like x3 or whatever, is x at timestamp 0. So that's what x of 0 means. So x is, say, an input image, and the q is the probability distribution of the pixels of that image. What we have so far described, right, in the prior discussion as well, as a sequence of stats that kind of goes from, now we've described the reverse process in the previous discussion, but think of it as adding noise in each step to get to some noisy or very noisy version of the same image, right? So in X1, we add some amount of noise, X2 add some more amount of noise, X3 we add some more amount of noise, and each time, let's say this black box that we have is adding the noise. Now, in effect, if you recall, we'll talk about the backward process in a minute, but let's assume in this case, to get the math behind it, let's assume that there is a forward process where we add noise to an image, okay? Some assumptions that we make is that the noise added is a Gaussian noise. So that can mathematically be described as there's a normal with the image being the center of the distribution, actual image x at t, and x at t minus 1, which is the prior step, multiplied by the square root of 1 minus beta t, right? And I times, I is the matrix, times beta t, where x at t, which is the image at time step t, again, since it's math and this was how the math was originally described, the concept of time step and stuff comes in here. So x of t is the image at time t, if you will, or time step t, and this xt minus 1 square root of 1 minus beta t is the mean, and I times beta t is the variance. And these are the parameters of the probability distribution and the noise, which we assume is Gaussian, right? So these are essentially pixel distributions of the image, but with noise added. And the other thing to note is that beta t, which is the noise that we add and so on, is something that we assume varies in the range of 0 to 1. Okay? And here's the interesting part. If beta t is 0, then the variance is 0. And if you do the math here, beta t is 0, square root of 1 is 1. Therefore, xt is basically identical, or is essentially normally distributed around xt minus 1 with variance of 0. That means, the next step is same as the previous step, right? And so this is a normal distribution with the mean being the mean of the prior image, right? Because beta t is 1, the variance is 0, so xt is xt minus 1 or a mean of xt minus 1, right? And flip it around, if beta t is 1, then the prior image kind of disappears, and what we get is pure variance, right? Beta t is 1, I times beta t is I. Therefore, what we have is pure noise. So what we are doing is, as we go through the forward steps, what we're doing is we're adding noise, and the amount of noise can be 0, in which case the next step is very much a mean of the prior image, or it can be all noise, in which case the next step is completely noisy and has no dependent on the prior image, right? So that's kind of what is happening in this process of adding noise, starting with an image and getting to xt. Think of xt minus 1 as just the step prior to this, right? So that is the process of forward diffusion. Now, interestingly, this particular forward diffusion process is described as a Markov process, and Markov processes, again, if you get into the details of Markov distribution, Markov process, essentially just a process depends just on the past, right? And this forward diffusion process is apparently described as a Markov process with Gaussian transition. The Gaussian transition is because we assume that the noise that's added is Gaussian in nature, right? The reason we do all that is to say sampling from a Gaussian process is easy, right? Why? Because we know the parameters of a Gaussian distribution. We know the mean and we know the variance. So once we know the mean and the variance, then it's easy to sample from a distribution, right? So that's kind of the reason, if you will, of choosing Gaussian noise or Gaussian transition. And it's mathematically determined that this process that we just described is a Markov process. That's mathematically the foundation. Now, interestingly, a lot of generative and, in fact, unsupervised learning is essentially trying to figure out ways to describe distributions in such a way that we can sample easily from them. Because if we can sample from them, then we can use a lot of math to get towards what the underlying distributions are, right? There's a whole course in Berkeley on unsupervised learning, and there are descriptions in that course of relevant portions of math that if people are interested that I can point to. But in this concept, again, keep in mind that what we have described by adding noise to image and getting from x0 to xt is a forward diffusion process. The forward distribution process is a Markov process with Gaussian distribution, a Gaussian transition, right? Now, the forward distribution can go from x0 and we can, all the way to xt, and 0 can be 0 and t can be 1,000 steps, okay? In order to get from an image with some amount of noise to an image which is purely noisy. Remember again that we're going forward, which means we're going from some image which we know what it is and having a little bit of noise to a completely noisy image. Okay, now what was discovered apparently in the 1950s, interestingly, in math, they obviously didn't discover it with the intent of providing diffusion capabilities, but fascinatingly, what was proved, it seems, in 1950 is if there is a forward process, which is a Markov process with Gaussian transitions, then it apparently is proven that a reverse process exists, and it is of a similar form to the forward process. That's fascinating and incredible discovery if you think about it. So if we have a forward process, which is a Markov process with Gaussian transitions, the genius mathematicians in 50s proved that there exists an equivalent backward process with an equivalent form, which means that it is also a Markov process with Gaussian transition. Now, what we don't know is what are the mean and the variance of the backward process. So the reason we chose Q interestingly, as the forward process probability distribution is because we actually are interested in the diffusion process to getting back the original image from the noisy image. We are not interested in taking an image and adding noise to it and getting to complete noise. Great, so what? But we are actually interested in taking a complete noise and extracting, quote unquote, extracting my word, but whatever the process is, of diffusing the original or desired image from pure noise. And what this math Markov process with Gaussian transition backward process is a probability distribution of P. Now we are going backwards. So we are trying to get xt minus 1 given xt. The forward process is xt given xt minus 1. The backward process is xt minus 1 given xt. Is also normal with xt being, the thing we desired, or sorry, the thing we already have, and a mu and a variance, right? With the mean and the variance being unknown. So if 2 is the forward path, P is the backward path, our goal now is, in order to extract, again, my word extract, but in order to diffuse, if you will, the image that we desire, what we want is to find out the mu and the var. Okay, so that is the problem that we're trying to solve. Again, if we don't know something, one of the things that we do in math is kind of trying to solve equations. The equation we're trying to solve is this particular one, or the distribution, probability distribution, of which we don't know the mean and the variance. So we're going to call it mu and var. Right? What we can do is determine the parameters mu and var. So how do we go about doing that? Well, in theory, maximizing a likelihood function enables us to find the mu and the var of the equation, the probability distribution P that I just put down in the previous slide. But keep in mind that we are talking about images, we're talking about incredibly number of large dimensions. So we are talking about integrals in God knows how many dimensions. That is a very tough mathematical problem to solve. And we need to solve it not just in a single step or one step, but we have taken through the forward diffusion process in taking an image which has some amount of noise and converting it to a complete noise. We took it through, let's say, 1,000 steps. Then we need to go back to 1,000 steps. So we need to find mu and var for 1,000 steps. That, again, is an incredibly hard problem to solve. So, math folks usually have a couple of standard tricks in these kind of situations. They try to reduce a problem to a somewhat simpler problem. So instead of likelihood, make it a log likelihood, because log likelihood has some advantages. What are they? Well, log is a monotonic function. They are trying to do it over 1,000 steps and the product of 1,000 things. And product of 1,000 things, when we take a log, makes it a sum of 1,000 things, and sum is a lot simpler than products. So products can be reduced to sum. Secondly, we are adding or making the assumption of adding Gaussian noise as we move forward, and therefore assume Gaussian noise as we come back. That's the 1950s proven theorem. So one of the things advantages of when we use log is the fact that log has exponential, and when you take log, the exponential is e to the x, then it becomes x times e to the stuff. So it gets eliminated by taking the log. So that's some of the advantages of using a log. But okay, we've done the log, but we still have this problem of thousands of steps over God knows how many dimensions. Again, still very difficult to solve. Comes another trick mathematicians use often is, if you have a very, very difficult problem, very challenging problem to solve, they just solve the closest solvable problem. And as long as the solution gives you the answer to what you seek, good enough, and you've done it. So that's the way that this problem was tackled initially, which is, and again, as I mentioned, if you want to really get into the math of how the evidence lower bound solution is equivalent to solving the maximum likelihood problem, I highly recommend watching a particular video of the unsupervised learning course that Berkeley has. I'll provide the link if you're interested in Slack channels, but that's a lot of math which we don't need to completely understand. All that we need to understand here is, instead of solving this very difficult problem that I was talking about, one, we reduce to log, but log is still a difficult problem to solve. So we just solve the problem of evidence lower bound. And solving the evidence lower bound under the condition of Gaussian distributions is actually easy to do, primarily because of the Gaussian assumptions, because of the math that falls out. So optimizing the elbow is, as it is known, evidence lower bound, is equivalent to solving this log likelihood problem. So what we do is we optimize the elbow, and it's as good as optimizing the log likelihood. So what we have done is, remember, through math, we first said, let's establish going from a noisy image to a complete noise. That's the forward process. Assume noise added is Gaussian. Along comes 50's algorithm, which is going backward, is equivalent process. If you have the markup process with Gaussian transition, we wanted to solve that, but it's impossible to solve. So we try to solve max likelihood, convert it to log likelihood, still very hard to solve. Well, solving elbow is close enough to optimizing elbow is close enough to solving that problem. So we optimize elbow. Now, this was the state of affairs around 2015 or thereabouts. But along came 2020, before that. So what we do now is we use two independent neural networks, one to predict mu and another to predict var, okay, of the backward process. So keep in mind, forward process, we go from the image A with some noise added to complete noise. Backward process, we start with complete noise and we want to get back the distribution, recover the distribution. So in effect, optimizing elbow with two neural networks predicting mu and var of the backward process as we go through the steps is, we start with pure noise, keep calling the two neural networks, sampling from the normal distribution, and applying that iteratively, right, to discover, if you will, or recover the distribution that we seek, which is the probability distribution of the original image. Now, something in the math description that they kind of get into, but this is my guess of what it means. I'm not 100% sure about it, and if any of you are familiar, feel free to chime in and explain better. But what they say is, look, when we go through the backward process, what we are recovering is the whole distribution. Now, they don't quite explain what the whole distribution is as opposed to a particular image, but here's my takeaway from what I would intuitively understand it to be. I believe, and Sujit, others, if you're familiar with the math in great detail and can correct me or expand on it, feel free to do so. But the point is, we are recovering through the backward process, I believe, the entire distribution of m-ness digits in the particular example that I was explaining. We're still not able to extract by this forward or backward process, or the backward process, I should say, a particular digit, unless we do all the other things that we talked about, which is giving the input, which we haven't done here, but we did in the prior description that I went through, which is provide some encoded value of the one-hot encoded indicator of the actual value. So in this case, what we are, I think, able to discover when they say or recover the whole distribution is distribution of all of the m-ness digits, which, while interesting, is not what we are actually after. But let's kind of, understand the process at again, the math behind it at an intuitive level. So here in this particular stage, if you listen to the lecture, they say, well, it helps us gain the whole distribution, but not necessarily the single image, because the process, the forward and the backward, operates at the distribution. Any thoughts on my explanation or my interpretation of what they seem to mean? If not, go ahead and feel free to comment.
Yeah, so I was thinking that maybe, if you know the whole distribution, you can sample from it and get back in this case, MNIST images. So you will get back specific instances of the MNIST images, but not necessarily the one you are looking for, right? So it's very similar to, how even in text LLMs, you ask for, say, you ask a question and it gives you different answers at different times, right? There is like, what's it called? Randomness in the answer. So yeah,
some variance in the output.
Right.
Thanks. So what we've done is by optimizing elbow, we are trying to match the power distribution, and we are trying to optimize to those distributions that we saw in the forward process. So that's essentially what we're trying to do as we try to go backward. So as we go forward, we add some noise, and as we come back, we're trying to match the distributions as we go backwards, right? And whenever we hear the term in deep learning, unsupervised learning and stuff of matching distribution, immediately the thing that comes up is KL divergence. So KL divergence is a function, and you can again look it up. There are excellent explanations of what KL divergence is and the map that corresponds to it. For Gaussian distribution, it comes down to very specific expression of probability distributions, but keeping those details hidden, essentially KL divergence, think of it as a function that can be used to compare and thereby get distributions closer to each other, right? Now, the map of KL divergence for Gaussian distribution is much simpler. It can be analytically calculated. And because we have made that assumption that the noise we add is Gaussian, we can do, under these restricted circumstances, using KL divergence, we can minimize the KL divergence between the distributions, therefore begin to get, during the backward process, what we are trying to accomplish. Right. Then, so therefore, and this was the state of affairs in 2015. Along came 2020, and what the paper
could you step back a slide? I was confused between the use of KL divergence in this slide. Yeah.
What is the confusion?
I was confused between the matching distributions, how it's being done by the KL divergence.
Yeah, basically, think of it when he's just saying that, optimizing elbow, if you actually dive into the math behind it, these two paragraphs are equivalent. The way you optimize elbow is essentially, another way of saying it is you minimize KL divergence between the distributions. So these two things are equivalent. That is, when you optimize elbow, it's same as minimizing KL divergence between two distributions. So what we are trying to do conceptually is we're trying to match the distributions as we go backwards to the distributions that we saw as we went forward. That's what you should take away from this explanation. The details we will look at as we go into the course more. Now, the interesting part is this, that along in 2020 came the further simplification of this whole process. So remember that we were trying to, with two neural networks, learn mu and var, right, which were unknown as we tried to go through the backward process. But along in 2020 came yet another paper, and you can look at the discussion of what the particular paper was. But essentially, it said, make some more simplifying assumption. Assume that the variance var is constant from step to step. So we don't have to learn it. We don't have to have a dedicated neural network to predict it. Also assume that the steps we are taking of adding the amount of noise, the steps we are taking, in other words, the variance of the noise that's added in each step is constant. So again, don't bother to learn beta t. Under these two conditions of where these two, we don't have to predict var, the step size is constant, so don't bother to learn that either. And therefore, all we are left with is learning the mean and setting var and beta t to some desired constant parameters. All we need to do is have the network predict the noise, or more precisely, have the network predict the mean of the noise, the mu. Okay. Under this condition, the loss function turns out to be just a prediction of the noise. So what we have done through the simplifying assumption is, during the backward process, we have a network, and the network's goal under the simplifying assumption is just predicting the noise in the image. Okay. And if we do that, then we are good enough to go on the backward process. So what we have arrived through these mathematical discussions and stuff is the process of denoising the image. That is the backward process that I just went through of eliminating noise from the image, right? In the case of Gaussian noise, is exactly equivalent to learning the score function. And learning the score function is just another term for the delta x3 or nabla x3 over x3 that I described in the previous discussion. So basically what we are saying is, in the backward process, the denoising thing that we discussed, that is, what Sujit also described of, hey, cool, we just take the noise, have the network predict the noise, subtract the noise, go through these steps multiple times, and voila, we recover the image. Well, guess what? That process is the same, equivalent to predicting the noise, which is essentially predicting the noise is taking the gradient of the log likelihood and subtracting it, right? So what we have come to through all this math and also on is to say that when we do predicting the noise, we have two different frameworks by which we can understand it. One is set up a probabilistic framework using log likelihood, elbow, KL divergence, optimize elbow, minimize KL divergence, and get to the solution. After 2020, with two simplifying assumptions, essentially it reduces to predicting the noise. That process is exactly equivalent to calculating the score function. So there are some papers which kind of use the first framework to describe the whole process. There are some papers which use this score function, which is whenever the term score function is used, at least in my brain, it snaps to, oh, this is the delta x3 by x3 process, gradient of the log likelihood, and using that information to sample from our distribution. And this is how the two framework approaches are connected. So there's some literature about the probabilistic likelihood perspectives of diffusion models, and there is some literature about the score function-based perspective of models. And the two approaches therefore have similarities and they connect with each other, right? So again, quick recap. I at least find this to be something that I like to take away from the whole discussion. You start with the data distribution we want to model, which is the, x0. The forward distribution adds noise to eventually end in complete noise. Because we add noise in a particular way, that is, we assume the noise is Gaussian, so Gaussian transition, Markov process Gaussian transitions. Thanks to math discoveries, the reverse process has the same form. We know how to train neural networks, two different neural networks, from likelihood to log likelihood to elbow to KL divergence, and optimizing elbow, minimizing KL divergence. Therefore, we are able to do that, but make a couple more simplifying assumptions, eliminate beta t to be learned, eliminate var to be learned, and then come to this amazing conclusion that all we need the neural network to do is predict the noise. This whole probability description is exactly equivalent to predicting the noise, which is nothing but learning the gradient of the log likelihood. So if you kind of recall these, I don't know, whatever, 6 or 7 steps, you have an intuitive math grasp of the process that we go through in Stable Diffusion. Lot more to go through, but that is what I took away from lesson 9 and 9B.
Yeah, very cool overview. Thank you very much. This is great.
Yeah, thanks, Srinivas.
Okay. Any questions, comments? I have to rush to the Kaggle group in 5 minutes too, but
Okay.
Again, a request and a pitch. Please feel free. Sign up. Next week we'll go through a somewhat deeper dive using the notebook, and I'll try and cover much of that lecture and probably the additional 9A lecture where John Whitaker goes through some of his notebooks. But beyond that, I'd really appreciate it if other people can sign up and take us through some other remaining lectures.
Yeah, I will. I actually have to, I just started doing lesson 9 before today. I think I started earlier this morning, in fact, sorry. But I need to go through, get a more of a skim through the different lectures there. So, and then I'll update some of the
Sure thing.
others.
No rush. Yeah. Just a general pitch to anyone to sign up, and all you need to do is watch the course ahead of time and be the guide.
Right.
Okay, feel free to comments.
So your the last part, that was your own, right? It wasn't in lesson 9. Kind of your.
It's there in lesson 9B. If you look at there is a video around lesson 9B. Yeah.
Okay.
I covered that as well.
Thanks.
All right, I think we can. Yeah.
Okay, good deal. Thanks, everybody.
Thank you.
Thank you. Yeah. All right, thanks.
Bye.
Bye.